Good afternoon, everyone. Welcome back to NPTEL live session for Advanced Transition Metal Organometallic Chemistry. Sorry for the preponement of this session. That was scheduled for tomorrow, but uh, this we are having it today from 12 to 2. And in this session also, we'll be talking about the concepts, the topics that have been covered for week 5, that is from lecture 20 to 25. Sorry. After that, we will be solving the questions that we have in an assignment. If there is any question or doubts from the previous sessions, please let me know before we start the session. We'll be starting the session in maybe 5 or 6 minutes. So yeah, please let me know if you have any questions so far. Thank you. So we can start the session. So the topics that we are going to cover today are so last time we ended up discussing about the transition metal cyclopentadienyl halide and halide complexes, basically how they are prepared and how is the reactivity. Now we will be moving to some another ligand, which is arene ligands. So we know that arene ligands general formula. So we will be talking about the transition metal arene complexes. So we will be talking about their preparation, their bonding properties. Also, we will be looking into the reactivity. So it is a similar kind of uh, trend that we have done with other ligands. For example, for cyclopentadienyl, uh, for normal cyclobutadiene. So similar thing that we are going to do with the arene thing, arene complexes, where will be talking about the preparation methods, bonding, how the ligand orbitals come in picture with when they get in contact with the metal orbitals, and then their reactivity. So generally, arene, we know we define them as C6H6, a derivative of C6H6. You can take a benzene example, you can take any derivative of benzene, but a symmetric one. So moving ahead with that one, we will be talking about the bis arene complexes. This is also one important topic, interesting topic, I would say. Metal complexes, and similarly, we will be taking its preparation and reactivity into picture, structure and bonding, followed by the preparation and structure and bonding, followed by their reactivity as well. So reactivity of these transition metal complexes plays a lot of role, and that's an interesting topic. So we will be taking into the picture, and at last we can see the preparation for arene metal carbonyl complexes, meaning besides arene, there is another ligand present in the complex, which is carbonyl, and we will see how it forms. In earlier cases, we have seen how carbonyl group has been removed or replaced by nitro group. For example, two three carbonyl groups can be replaced by two nitro if nitrosyl has been bound as a linear in a linear fashion, because carbonyl group will give you two electrons and linear nitrosyl will give you three electrons. So three carbonyl groups is equals to two nitrosyl. Similarly, if we have benzene or arene rings, and when we are treating it with the metal salt which is having carbonyl already, how it is going to form, and how many carbonyls can come into picture. So we will be looking into those things today, and at last we will be talking about the problem session. So here is your time. If you have faced any difficulty in your previous sessions, please let me know. Otherwise, we can just continue with our today's topics. So it is more or less similar what we have seen with the pentadiene, cyclopentadiene. So let's start with the first topic, which is your C6H6 as a ligand. So you know about benzene. Now how it works when it acts as a ligand to the metal and their complexes, arene complexes. We are not mentioning benzene here because it can be substituted also. So we are giving a general term of arene. So in this one, transition metals, they have a very strong interaction, or you can say bonding with arene groups, and also they make a variety of a large variety of eta 6 arene complexes and derivatives. However, if we see main group elements, the one that I'm highlighting in red, meaning it is having weak interaction with the arene molecule. Sorry about my writing today. So these are the two features that I wanted to highlight, is the interaction of the arene ligand with your transition metal. So this would give you a strong interaction and a complex, calling an arene complex, whereas it fails to have a strong interaction with the main group elements. Now moving towards its preparation method. So in the preparation method, we have a general and named reaction, which is Fischer-Hafner synthesis, might be known to you as well. So when we take 3 moles of chloride heated with 2 aluminium, 6 arene molecules, in presence of Lewis acid, AlCl3, and water, it would end giving you 3 moles of arene, twice, chromium plus, and aluminium will be oxidized to aluminium 3, right? When this molecule has been formed, this then undergoes reaction with Na2S2O4 in KOH. It would end forming eta 6 arene 2 chromium, a kind of sandwich molecule where instead of the CP you have arene group. And this is the procedure how we can get a bis arene metal complex by involving substituted arene in presence of Lewis acid. There are certain conditions that we need to keep in mind when we are synthesizing these types of transitional complexes. So the one thing that we have in mind is, so there are some limitations of this Hafner process. The one limitation, this I'm writing it in red, that arene should always be inert towards AlCl3. So in presence of clear acid, it should not undergo any kind of side product. So it should be inert towards AlCl3. If we are using alkylated arenes, then they will undergo isomerization by AlCl3. And the third part that we have is, if we have heteroatom substituted arene, they will form Lewis acid or base depending upon the way, the nature that they are having. And it's with AlCl3. So we need to be really careful when we are using AlCl3 and the substrates, because it should be not, it should not undergo any kind of Friedel-Crafts acylation, alkylation when we are treating it with Lewis acid. If at all we are using alkylated arenes, it will undergo isomerization in presence of AlCl3. And if there is any heteroatom substituted arene is there, it would form a reduct with AlCl3. So these are the main limitations, or one can say that these are the things that we need to be very, very careful and need to keep in mind. Okay, let's move to the preparation method, which is your cyclomerization, cyclotrimerization of the alkynes. Since we are talking about the arene, sorry about that. So we are starting with first preparation method, which is cyclotrimerization of alkynes. Where if I'm treating it with, if I have a cyclopentadienyl complex with chromium, 3 molecules chromium in TH3, it is a octahedral. And if it is not defined, like which hapticity has been given, you should always take the hapticity one. If it is not defined. And then you are treating it with alkyne. In the medium of THF solvent at 20 degrees. Then on treatment with water and oxygen, you ultimately end up ultimately end up. So we have already seen earlier. If we have C triple bond C, CH3, and we have 3 molecules like this way, and another one is this way. Okay, so this pi bond will go and make a bond between this CH3, this C to this C. Then this one go and bond with this one. And then this will go and bind with this one. So ultimately, if you'll see A, B, C, okay, I'll write with a different pen so that you can see that. This is A, this is B, this is C, this is D, this is E and F. Now you will make a benzene substituted arene. So if I'm starting with A, B, C, D, E, and F, so all the 6 sides, there is one substitution. And since it's a benzene ring, it is aromatic as well, down to nature. I hope this is clear, like how cyclone trimerization of peptides work. If there is any doubt, please let me know. Okay. So if there is no doubt, we can move ahead with our next preparation method. So our next preparation method is reductive complexation. If you're taking a complex of metal chloride and THF molecule is completing the coordination number, it's just a solvent molecule, and you are treating it with N molecules of lithium C10H8, it would end up doing a reductive complexation, and you will end up having eta 6 C10H8 full rise M percent times lithium chloride. So here we are taking a naphthalene, but how it comes under the category of transition metal arene complexes, because we are talking about a hapticity of 6, that too cyclic rings, aromatic ones. So here when we are mentioning that the hapticity of 6 is there in a naphthalene molecule, which is an aromatic one, so it would form a transition metal arene complex, in a reductive complexation panel, where the reduction is happening using a lithium C10H8. So the ligands that which readily forms radical anions are best suitable for this method of synthesis. So that we need to keep in mind what kind of ligand which can undergo a radical anion formation and can interact with the metal center quickly. Right. So at this point we can highlight over here. So the ligands that readily forms radical anion, they are best suitable for this synthesis. Okay. Now moving towards our third method. That's a third progression method, which is vapor condensation, co-condensation, short form CC. If I'm taking a titanium in gram scale and I'm treating it with two molecules of benzene in grams, then if I'm doing a co-condensation at 100 and minus 196 degrees, it's a very lowest temperature, then 25 degrees for stabilization, that means room temperature, it would end up giving you a sandwich complex with two arene rings at top and bottom. So this has been given by Green in 1973. So this is another method of synthesizing the complex. Their structure and bonding are more or less the similar. You already have the lecture slides. If you have any doubt, please let me know. We can quickly move to the structure and bonding. How sigma and pi look like in case of early molecules. We know that in ligand and pink one we are taking this metal. So in ligand, if we are talking about a sigma, we have 6 orbitals over here. And the first half is filled. This would interact with s orbital, A1G. Another type is also there. I'm just giving an example like how sigma bonding works. So this is for the sigma bonding between metal and the ligand. The ligand is a ring ligand. Also, it can form with your dz square, which is having an electron density right along the internuclear axis. And if you have A to U, because since it's a ring, we are talking about base ring, so there has to be two rings in A1G. Since it's a symmetric, so everything would be symmetric. Here, if I'm talking about A to U, that means inversion center is gone. So if one center is like this way, upper lobe has been filled, then the other triangle that we have, the lobes would be opposite because of the U sign symbolizes that there is no inversion center. And when these ligands, they can combine with your PZ orbital, this will make a sigma bond too. Similarly, there are pi and delta pi bonding, where dyz and dxz is there with E1G and E1U is there for py and px. Y for d orbitals, it is giving as G, and for p orbitals, it is giving as U, because d orbitals themselves have a, if you draw their shape, they themselves have invergent center in with them, whereas which is missing in case of px and py. So this you can go and check out. Also, there is one comparison between ferrocene, FeCp, and iron chromium. We can take iron C5. Sorry about that. C5H5. That bond is having greater energy compared to the D chromium CC6. This is 170 kilojoule per mole per ring. This is 260. So this was one such example. And then we have some reactivity questions. So in contrast to the metallocene, the metallocene that we saw, that was undergoing electrophilic substitution reactions, whereas in case of viscerines, they do not undergo these reactions. Instead, the central metal that gets oxidized, if it is being treated with electrophile, therefore no further peripheral electrophilic substitution. That means no substitution will further occur at the uh, arene group. Only the oxidation will happen at metal position. And another point that I mentioned at the end was arene metal carbonyl complexes, the preparation when we are treating it with molybdenum CO gold 6 at 125 degrees. So since this particular molecule can give you, if it is binding with beta 3, so it can give you these electrons. It would bind as beta 6 and it would give you 6 electrons. Each CO gives you 2 electrons, and if you are replacing 3 COs, that will give you 6 electrons. So I hope this is clear. If not, please let me know. If you have any questions, then we can move for your problem sessions. If there is no question, then we can move to problem session. Okay, the first question that we have is the common method that we use for the preparation of biserine metal complexes is an R. We know that we have oxidative reductive cyclization that we have seen, complexation, sorry. We have also seen vapor condensation. So what is the expected answer from your end? So what we have seen is three methods: reductive complexation, cyclotrimerization of alkynes, and vapor condensation. So the option A and B are correct. You can go back and check the lectures. If you need any more examples, we can have it in. If you have any doubt, we can have it in next sessions. Now the second question is chromium Cl3 when it is being treated with aluminium with six arenes and we have a US acid. You can see the reaction is having an arene complex. What is really happening that aluminium is reducing and doing reduction and it's getting oxidization. So this is a example of Fischer Hafner synthesis. This is actually a named reaction which is Fischer Hafner. So the option C is correct. Moving ahead to the next one, which is alkylated arenes in Fischer Hafner synthesis. If we have this one, then you know that it would be isomerized by AlCl3 present. So this was quite straightforward. And the fourth one that we have is metal orbitals for this arene complexes, which has delta and sigma symmetry respectively if the Z axis is the molecular axis. So let's see for the sigma. Sigma, if you are having the Z axis as your molecular axis, so either PZ or DZ square. So just see the sigma would come onto the second side. This is incorrect, this is incorrect, this is incorrect. Only the option that is left is option B. And this is also correct because delta bond is being formed by dx4, y square and dx5. So our option correct is B, where PZ is going to make a sigma bond. Identify the doubly degenerate ligand of group orbitals for C6H6 ligand, which is centrosymmetrical in nature. So when the hint has been given in the question itself, you better find out the solution there itself. If it is asking about the centrosymmetry, that means you need to see G or U symbol that has been given for your term symbols, or you can call them as a Millikan symbol. So you have E2U, E1G star, B2G, A2U. So we can cut down the U part because that is not centrosymmetric. We only are left with E1G and B2G. So this E defines that two irreducible representations are involved. For this, you need to go back and read your group theory. And B symbolizes for one reducible representation or the orbitals. You can understand that two molecular orbitals would be involved here and there would be one orbital. So when we are talking about the doubly degenerate, then we need to go with this E1G because that is two only. So option B is correct. I hope this is clear. Now, the next question that we have, the following reaction can be categorized as what? When we are having a substituted arene with iron system, and there is R minus, where you would expect it is going on to and attacking onto your arene. And this is nothing but your nucleophilic addition reaction, where nucleophile is attacking onto your ring and the reaction is proceeding by having R substituted arenes at the end. So this is your nucleophilic attack. Sorry. The point group of the following compound. This is a question that for the other courses as well. So sometimes it is very important to know. It is actually always advisable to know the group theory, know the point groups because that would let you to know about their symmetry, their orbitals that have been involved, and therefore the bonding becomes even more feasible. So this is a D6H. You can see, find out all the elements that are present. It would be having C6, it would be having 6C2, it would be having sigma H, so on and so forth. Therefore, this is your D6H. Now here when we are having a chromium 0 and it is getting oxidized to chromium plus dot. So this is basically the attacking species is your radical, because in presence of radical only it would undergo this kind of reaction. So alkyl radical, option C, that was straightforward. Now the next question that predict the following. This also is one of the examples that have been told by the professor that generally when lithiated arenes are there with the vanadium complex and some other germanium chloride salts have been used. So it would replace the lithium and two lithium LiCl will precipitate out and we will end up having this kind of complexation. And the last question that we have is the bond energies. Since we are comparing arenes and CP, obviously this makes a stronger bond and that's 260 kilojoule per mole, whereas chromium C6H6 is 170. So option B is correct. Please go through whatever we have done so far. And if there is any question, I'm happy to answer your questions. Thank you.